bulk modulus. We have to define bulk modulus of elasticity. In the diagram, we have a sphere of volume V1. So this is the sphere. This is the sphere of initial volume V1, and a deforming force F is applied normally on this sphere, on the surface of the sphere. This is the direction of deforming force, which acts normally with respect to the surface of the sphere. So in this way, deforming force are acted from all the directions with respect to the sphere. F is the deforming force. Due to application of this deforming force, volume of the sphere compresses and volume of the sphere decreases from V1 to V2. V2 is the final volume of the sphere due to application of the deforming force. When a deforming force F, in the diagram, F is the deforming force, due to application of this force, volume of the sphere decreases, is applied. When a deforming force F is applied normally on the entire surface, is applied normally on the entire surface of a sphere, when a deforming force F is applied normally on the entire surface of a spherical body, of volume V1, within the elastic limit, its volume decreases to V2. Its volume decreases to V2 due to the application of the normal stress, due to application of the normal stress or pressure, that is the change in pressure. Actually, in this case, the normal stress is equivalent to pressure, means change in pressure delta P, which is equal to the ratio of deforming force acting per unit area. That means delta P equal F by A within the elastic limit. Therefore, the bulk modulus of the material, the bulk modulus of elasticity of the material of the sphere or of the spherical body, the bulk modulus of the material of the spherical body is defined as the ratio of normal stress to the volumetric strain. The bulk modulus of the material of the spherical body is defined as the ratio of normal stress to the volumetric strain within elastic limit. Therefore, bulk modulus equal normal stress divided by volumetric strain. Bulk modulus equal normal stress divided by volumetric strain. Therefore, K equal F by A, which is the normal stress acting on the spherical body, minus delta V by V1, where delta V is equal V2 minus V1, which is the change in volume of the spherical body, change in volume of the spherical body. K equal F by A divided by minus delta V by V1. That is the expression of bulk modulus. The expression of bulk modulus of elasticity. Also, F by A is the normal stress, and which is equal to delta P, where delta P is the change in pressure. Delta P is the change in pressure. Delta P is the change in pressure on the spherical body. Therefore, K equal delta P divided by minus delta V by V1. K equal delta P divided by minus delta V by V1, which is the expression of bulk modulus of the material, of the spherical body. K equal delta P divided by minus delta V by V1. Negative sign indicates that the volume of the spherical body decreases due to the application of the normal stress or the pressure. That means volume decreases due to application of pressure, that is due to application of change in pressure. Delta P is equal F by A on it. If the pressure is applied on a spherical body, in that case volume increases. This negative sign indicates that the volume of the spherical body decreases due to application of normal stress or due to change in pressure or due to application of pressure. Here we can draw the diagram again. This is the spherical body, and a deforming force F is applied normally on the surface of the spherical body. F is the deforming force. Volume of the sphere decreases from V1 to V2. In this case, A1 is equal to A, which is initial area, and A2 is the final area. And change in pressure or normal stress is F by A, means deforming force by initial area. Delta P is the change in pressure, which is equal to F by A. Delta P equal to F by A is applied on the spherical body. Pressure is applied, or change in pressure occurs with respect to the spherical body, and volume decreases from V1 to V2. Volume decreases from V1 to V2 due to application of pressure or due to change in pressure. Due to application of pressure, due to change in pressure, volume decreases, and delta V is change in volume in this case. volume decreases. That's why you have to consider negative sign. In this case, due to application of pressure, volume decreases from V1 to V2. Now we can consider another concept, that is, if we have a sphere of volume V1 and deforming force is acted radially outwards, that means pressure is released and volume of the spherical body increases to V2. This is the deforming force which is applied radially outwards, and delta P amount of pressure is released. Delta P is the decrease in pressure or amount of release of pressure. Here pressure acting on the spherical body is released and the volume increases from V1 to V2. So in this case, the expression of bulk modulus K equal minus F by A divided by delta V by V1. In this case, negative sign is taken in front of F by A. Therefore, K equal to minus delta P divided by delta V by V1. Minus delta P divided by delta V by V1. And in this case, we have considered the negative sign as pressure is released. In the initial case, pressure was applied, but here negative sign indicates that if pressure is released, volume of the spherical body increases or volume increases. Volume increases. Another additional information, units of bulk modulus, unit of K or B is Newton per meter square. Number 2, Pascal. And dimension of bulk modulus, that means third bracket K is equal to M1 L minus 1 T minus 2. That is the dimension of bulk modulus, which is equal to the dimension of pressure.